Thank you. Sure. All right. So that's what we've got right there. And if we're looking at that, if we go all the way to our maximum displacement, what does the velocity become there? So if we're looking at a mass spring system, right, here's our spring. Here it is at maximum compressed. Here it is at equilibrium. So this is equilibrium. This is like, you know, this is X max in the negative direction. And then we come out here to X max in the positive direction, right? We're on this mass spring system as it goes back and forth. If it's at one of the maximums there, how fast is it going to be going at that point? Zero. Because on its way out to the maximum, say it's leaving equilibrium and it's going this way, it's headed to the right. When it gets out to equilibrium or out to the maximum, it has to turn around and go the other way, which means at least for an instant, it has to come to a stop, right? Kind of like the ball. When you throw the ball up, at its highest point, its speed is what? If you threw it straight up, it's zero, right? And so the same thing here. So out here, let me zoom in here. Out here at the maximum, we have velocity equals zero, which means kinetic energy equals zero. And therefore out here, we have our position equals the amplitude, and therefore our potential energy is equal to 1/2 kA squared. And the same thing is true over on the other side. Where would this be going the fastest? In the middle, right? Because if you're at the middle, you have zero displacement, you have no forces pushing on and stopping it. So let's say you take this thing, you stretch it out to the right, and you let it go. It speeds up towards equilibrium, and then it hits equilibrium where the force becomes zero. And then as soon as it passes equilibrium, the force reverses direction and starts to slow it down. So it speeds up the whole way toward equilibrium, hits equilibrium. The force immediately then reverses as soon as it passes it and starts to slow it down. So it speeds up, slows down, stops. Speeds up, slows down, stops. And that's what it does going back and forth, right? So what we can do to get the total potential energy here, our maximum, is just to simply look at the point where we have no kinetic energy and we're at a maximum displacement. That's what that U max is there. All right, it's 1/2 kA squared, the amplitude. It's the maximum displacement you get. In other words, this equals 1/2 kx max. Maybe I should put that below it. I kind of squished it in there, huh? This is 1/2 kx max. It's our maximum displacement there. And then our kinetic energy max is just going to be equal ultimately to the same thing, right? Because what happens is when we get into this middle part, right? We don't have to go through all that. We can just conceptually do this. You get to this middle part, there's no more potential energy, right? Because the displacement for X is zero at that point, and therefore all the energy is purely in kinetic energy. Kind of like the fastest place when you drop a ball is right before it hits the ground, right? Right when it reaches the ground. Same thing there. Here in the middle, velocity is a max, and therefore kinetic energy is a max. Potential energy equals zero, right there in the middle. Okay? And then all of this stuff right there can all go right over here too for that side. All right? So they're the same. And so what this is telling us then, ultimately, is, and I'm going to kind of skip ahead here, is this. It's telling us that as one decreases, the other increases. You see that? All right, if your kinetic energy is in green, you stretch it off to the side, give it pure potential energy. You let it go. The potential energy decreases, 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 while the kinetic energy increases, increases, increases. What is this location? Where would you be? Where would you be? Right in the middle, right where you have a maximum velocity, right? And right where your potential energy is 0. Then it starts to slow down and lose kinetic energy while gaining potential energy. It's swinging to the other side, right? Where would you be right here? At one of the maximums, at an amplitude, right? The left or right or up or down, right? And then it just keeps going like that as they keep swapping back and forth. If you add these two up at any point, like say you look right here in the middle, you add it onto there, it's always just going to add up to be that total energy there at the top. All right. And we can see that by going back a page and taking a look here. If we add them together, you could take a look at this, are 1/2 kx squared and 1/2 ka squared, right? Well, we can go through them and find those positions, right? And when you do that, one of them is going to be cosine, one of them is going to be sine for position, right? One's velocity, one's position. So it doesn't really matter which one you do. It just depends where you started. If you stretch it all the way out to the side and start it, then position is cosine and velocity is sine. But if you come along and it's swinging and it's right in the middle when you first start looking at it, then it's the other way around. But anyway, one of them is cosine, the other is sine. Doesn't really matter which it is because they're both that 1/2 kx there. They're flip-flopping. So they're just swapping like that. And if you see you go through and add those two up, you get the 1/2 ka squared as your total. But that's in both. One's doing a sine while the other is doing a cosine. Okay? They just keep flip-flopping back and forth. And what I mean by you could flip-flop them, if you look at this here, you see that the one in red, the potential energy, what is that? Is that what kind of a graph is that starting up there? That's a cosine, right? And so if you just moved over a little bit, you can make it a negative sine graph, right? If you came along and looked at it right here, then suddenly that red one starts from here and it looks like a cosine graph instead. That's what I mean by you can flip-flop them. And since they're squared, you don't have to worry about the negative part of it. Okay, any questions on that? A little bit of sense so far? Maybe? Okay. Pendulum. In fact, what we're going to look at here first is something called the simple pendulum. So it's a simple pendulum, consists of a mass M of negligible size suspended by a string or rod of length L of negligible mass compared to the mass of the pendulum bob. That's got to be kind of small in size. The angle it makes with the vertical axis varies with time as a sine or a cosine. Again, it depends where you start it, but sines and cosines are the same thing. They're just shifted versions of each other, right? And so we take a look at this. We come over here and you can see this graph here that shows us what the restoring force is. So if you look at this part right here, this is the restoring force. So if we want to decide, is this Hooke's law? Is our pendulum going to be simple harmonic motion? Okay, so we look at this and we say our force is equal to, and if we see this, if we take it and stretch it to the right, that force is trying to pull it back to the left towards the center, correct? So we essentially have that negative sign, right? We have that negative mg, and then it's a sine of theta like that. So we've got the negative part, we've pulled it to the right, we're letting it go, I'm totally neglecting this side over here. We've pulled it to the right, and it's pulling it back to the left. And if it goes and swings over to the left, the mg sine theta will flip around and pull it back to the right. So far, we have a force that's opposite in direction to the displacement. So that's good, correct? Now, what's the other thing we need? Or at least we can have. Right, what's Hooke's law? F equals negative kx. We've got the negative. What's the next thing? which is a what? Yeah, just some sort of constant we can have there. It could be 1, but there's some sort of constant we can have there. Hey, is mg a constant? There we go. So we have a negative, we've got a constant. All we need now is proportional to displacement. Now we have sine theta. Is that proportional to displacement? Sine theta? No. No, it's not. Uh-oh. This does not fit Hooke's law. This is not simple harmonic motion. That's not good, right? Since that's what we're talking about. Well, we can approximate. Take a look there at the sine of theta and then y equals theta. And don't worry about all this area over here. We're going to ignore that area. What we want to do is look at this area right in here. And what does it look like there? Yeah, they're pretty close, aren't they? What we're going to say is we're going to use what is called our small angle approximation. And we're going to say for small angles in radians, not in degrees, sine of theta is approximately equal to theta. In fact, if you wanted to, grab out your calculator and put it in radians, hit sine of 0.1, and you'll get like 0.09. Sine of 0.01, you'll get like 0.0099 or something like that. And like the smaller you make it, the closer they get together. So this is our sine approximation. In fact, if you've taken calculus, and you did the limit of sine of theta over theta, what was it? As theta went to 0. Anybody? My favorite answer? 1. It went to 1. Okay? If you remember that limit. So we're going to say sine of theta equals theta, and I'm going the wrong way, sorry. Go back over here. Now what we can do is make this an approximation. So for small angles, this is our simple pendulum, which is just a small pendulum bob, negligible mass, and a small angle. Those are the 3 things we need, a small angle. So for small angles, our force is approximately equal to negative mg theta. Now, does that look like Hooke's law? Negative, a constant, and then an angular displacement, right? In fact, if we just multiplied both sides by r, we would have mg, and then like by the length of the string, we would have exactly Hooke's law. We approximately have exactly Hooke's law, right? So you multiply that by L. So you could do something like, you could say this is F negative mg over L times L theta, where we have a negative, we have a constant, and then L theta is a displacement, right? And so that works very nicely. So for small angles, if you've done the lab and you're in there doing the lab and you started swinging it real big, what did I say to you? Small angle. Because if you do a big angle, it's not going to work. And the larger angle you do, the worse it gets. In fact, you see that right there. The larger angle you do, the worse this approximation becomes. So how small of an angle do you have to do in order to use this approximation? It depends how accurate you need to be, right? If you're playing some putt-putt golf course where they have some swinging pendulum and you just have to time the golf right and it's swinging pretty big, you probably don't have to worry about being too super accurate with it, right? But if you're designing some sort of clock and you need it to be like super accurate, because even if you're off by like 1/100th of a second every minute, your clock is going to be off very quickly, right? It's going to be off by minutes within a day. All right, you're going to need it to be more accurate than that, so you're going to want a smaller angle, right? You don't want your grandfather clock swinging like this. They swing a little bit, don't they? They have a very small angle, and so it gives you that good approximation. So the more accurate you have to be, the smaller it has to be. I've seen some textbooks say less than 6 degrees or less than 10 degrees or something, but you know what? It just really depends on how accurate you need to be. If all I need to do is get approximately how long it's going to take it to just make one swing, like to within a second, then I probably don't have to worry too much about it being a small angle, really, right? Okay. So take a look here. As I showed you just a second ago, we added L back into it, right? Back over here. It was mg over L in the place of where K was. So you come back over here, we're taking this same period, 2 pi square root of m over K, but we're replacing K with mg over L because that's what's in the place there now, right? And so when you do that, look what happens to the m's. What'd they do? It's a C word, ends in ansel. They canceled, right? Good, they're gone, which means, of course, if you've done the lab already, if you haven't done the lab yet, if you're in Thursday's lab class, just don't listen to this part right now. You should have found that the mass didn't matter, right? The mass didn't matter. And here you go, it canceled out. It's independent of the mass at the end of the bob, or the mass of the bob, okay? And so we end up with period, right? Period equals 2 pi times the square root of L over G. So if you design a grandfather clock, right, just based on this, and it works good enough, I shouldn't say works perfectly, but works really well here, takes a long time, a year before it gets to be off by any appreciable amount of time, and you took it to the moon, what would happen to that grandfather clock? It wouldn't be the same, right? What would be wrong with it? The period would be longer because we'd have a smaller G, right? On the moon, right? It's like 1 point something, 1.6 or something. I don't remember. 1.3, I don't know. G would be smaller. If G gets smaller, we have a smaller number on the bottom of our fraction, we get a bigger number, right? So as that denominator gets smaller, our period would get longer. The pendulum then, instead of it swinging like this, say going there and back every second, it's going to do this. It's going to go slower, right? So what happens to your grandfather clock? Does it run fast or run slow? Run slow. The period gets bigger, it's running slow. It's not going to keep good time for you anymore up there. Okay, you'd have to rebuild it, re-gear it or something to make it work properly. All right, is this making sense? We doing okay? How am I doing on time? All right. Doing okay so far? All right, so that is the simple pendulum right there, the small angle pendulum sometimes called. Now here is a physical pendulum. This is one that is not that little simple pendulum. You still typically want, you know, the smaller angles. You don't want these big ones, but these are actually just, you know, kind of more realistic. Like if I were to let this pen, you know, swing like this, okay? Not just a string with all the mass down at the end. And so you can't just model it the exact same way. I'm not going to go through all how you model it, but basically you end up with this right here for the period. Okay, 2 pi square root of L over G, which you should be able to cancel one of these L's with the ML squared on the bottom, but you typically don't want to do it because you have that moment of inertia up there. What is moment of inertia? Actually, who can tell me what is inertia? Well, that's that. What's just inertia? There you go. I like that. Resist change in motion. It's the property of matter to resist a change in its motion. Okay, so that's which of Newton's laws? Third is every force is equal and opposite force. Second is F equals ma. We'll get there. First law. Does it matter if you remember the order of them? Yes, they're ordered from what is considered most fundamental to least fundamental. In fact, if you go into thermodynamics, how many laws of thermodynamics are there? Why is it the 0th law? Because they made the first 3, they made 1, 2, 3, and then they decided the 0th law was more fundamental. So they went back and put it in the front and made it 0. All right, instead of bumping it up and make it 1, 2, 3, 4, they left 1, 2, 3, and they said, all right, we'll make this 0. It's more fundamental. So it does tell you the fundamental order of them. Okay, so the first law, remembering the order does help because you get that order of what's most fundamental. Probably at this level, it's not that big a deal, but if you really go way deep into it, it starts to be something you want to consider. So anyway, inertia is tendency of an object to avoid a change in its motion. What do we measure inertia in? Anybody remember? If I gave you an object and I said, measure its inertia for me, what would you do? That's right, you'd stick it on a scale and measure its mass. Mass is a measurement of inertia. It tells you how much inertia something has, right? If you want to know how hard it is going to be to stop something that's flying by you in space, you want to know its mass, right? If I walk up and, push a golf ball with the same amount of force that I walk up and push a dump truck, which one's going to move much more easily for me? In other words, which one is going, well, I should have said, which one's going to not move as much? Which one's going to avoid a change in its motion more? The dump truck, because it has a greater mass. Okay? So mass is a measurement of inertia. What is moment of inertia, Casey? No, just a general idea. Resist a change in its rotation, right? So inertia is a resist a change in just regular linear motion. Moment of inertia is a resistance to a change in how it's rotating. If it's rotating, it doesn't want to stop, and if it's not rotating, it doesn't want to start rotating. Okay, but that's the idea there, and that's what moment of inertia I is right there. And it's going to typically be some type of m times r squared, and there's some constant out in front. You usually look at a moment of inertia table, right? Y'all did this last semester, right? Okay, and so that's where you're going to get that. So you get that L squared in there, and it'll cancel out. If you go down right here, if you substitute moment of inertia of a point mass, which is what we were just doing with a simple pendulum, look at what you end up right back with, right? The moment of inertia of a point mass is just mr squared, in which case r is the length of the string, so ml squared, they cancel, and you're left with 2 pi times the square root of L over G. Okay? We're good there? All right. Next, damped oscillations. So far, we've been talking about oscillations where we are frictionless. What happens if we're not frictionless? Well, we get damped oscillations. We get damped harmonic oscillations or damped harmonic motion. Typically, the damping is proportional. Right here, what you see is proportional. Kind of looks like Hooke's law, but it's not x, it's v. It's proportional to its velocity and in the opposite direction, right? Because it's usually some sort of friction. Okay, and so we get negative b. B is just your damping constant, and it's going to be different for your situation. You don't have to worry about it. I don't believe you have any like homework questions on this or anything. It's just a conceptual idea here. But negative b times v, the larger the damping, the greater that b would be for a given velocity. And then it caused some sort of exponential decay. According to this, A amplitude equals the initial amplitude times e to the negative bt over 2 times the mass. So it's going to decay exponentially. The amplitude will decay. And it'll decay something like that. All right, and you can see the AE, this exponential decay in the overall amplitude. See, it keeps hitting it in whatever the new amplitude becomes, and the same thing down here. This is an example of what is called underdamped. So this is like, you start something swinging, like if you start a pendulum and it swings and swings and then eventually stops, right? It's typically underdamped. You can have 3 types of this situation. You can have underdamped, overdamped, and critically damped. So underdamped is what you just saw. It swings back and forth and slowly comes to a stop, and you know, however long it takes. Critically damped is where they typically try to make swinging doors that way, where it swings and just comes right to a stop, especially like or screen doors, you know, like a patio door. They try to get that to go out and then just come back in and just come to a nice stop, right? You try to adjust it just so it does that. That's critically damped. It just comes right back down and slowly comes to a stop. And then over damped, this is when you try to swing it and it goes open and it comes up and it can't make it all the way back. And it stops before it gets back to equilibrium. All right. If you have your door too stiff, it never fully closes, right? And that's over damped then at that point. So you have those three types of damping: critically, over damped, and under damped. Okay. All right. And this kind of damping is even what you want to do in your car for your shocks, right? You want a nice damping so your car doesn't hit a bump and just do this and keep bouncing. And so they do that by mixing together two different types of springs. One that's very stiff and one that's not as stiff. So one with a big K and one with a little K. And one will cancel out the high frequency stuff, that'd be the big K, and then one will cancel out the low frequency stuff, that's the little K. Or the other way around, I think I just said that backwards. Anyway. Okay, next, driven oscillations. We get to watch something here. I should probably pause this because I can't, it's somebody else's YouTube video. So let me pause it. All that stuff about swings and everything. I guess I have to repeat it now because I was not recording at the time, but you want to match the natural frequency with your driving frequency. If you do that, it'll build and you'll get resonance. It'll start to build up and get larger and larger. Again, like swinging on a swing, you got to match your legs and you're driving yourself forward and backwards to the frequency of the swing. When you first put a little kid on a swing, they're not good at it because they don't know how to do that. They just sit there and do this really fast, right? I remember having to try and convince my children that they had to figure out how fast that swing wanted them to go because they would sit down and just do that and wouldn't go anywhere. So just keep that in mind. Match that driving frequency and you get it. Okay? And there you go. Just another picture there of some oscillations with different types of damping that goes into it with your frequencies. And I think that's it for this chapter. The rest is just a summary of chapter 13, which you can grab on these notes and go through and just look at what equations we talked about, what situations we talked about, and anything like that. So do we have any questions here from anything for chapter 13 before we just work on some problems, see how many we can get through? No, that either means like absolutely everybody here understood everything I said because I did an awesomely great job, or everybody is so lost that nobody even knows what question to ask. Yes?
So our goal when we do oscillations is to get resonance of the ultimate idea?
Oh no, not if you're building a bridge.
Oh,
You don't want that, not if you're building a bridge. Not if you're trying to build something that's not supposed to be swinging, right? You don't want resonance then. If I'm trying to build a pipe organ, then yeah, I want some resonance, right? That's what's gonna, I make it a certain length so that the sound resonates at a certain frequency in it and I get a nice sound that I want. Yeah.
How do they do it with like the skyscrapers that have to have a little bit of like movement, but obviously not too much to really do that?
I think I've seen some, so let's keep in mind one, totally not an engineer. Totally not an engineer. I got a degree in physics. I once went and tried, I thought, I'm going to do a degree in engineering. The first class I took, they asked a question. I answered it totally in the physics way on this quiz. They asked like, what is voltage? And I went through and like derived out from Maxwell's equations what voltage was. And he handed it back to me with question mark, V equals IR. All he wanted me to do was write down Ohm's law. And I spent like a page on this. And so I was like, I'm totally in the wrong place. I am not an engineer. So I don't know the perfect answer for that. I know they do stuff with weights down in the bottom of it. I believe. They'll put like counterweights and stuff in there. So like as it swings one way, the weight kind of swings the other way and it kind of keeps it like that. So I think they do it a lot with hanging weights. I'm not sure if they still do that, but I know they used to. And I really only know that from watching like engineering shows. I never took a class where I talked about building a skyscraper. Kind of like I know that from watching shows about boats, they put giant spinning things on there to keep them from swaying too much, conservation of angular momentum kind of a thing. So they at least used to do it with basically big suspended masses.
Thank you.
Yeah. Yes.
I don't fully understand how gravity doesn't have an effect on a vertical mass spring system.
On a vertical mass spring system, why it doesn't have an effect on it?
Section 4.
Yeah. Well, let's think about that. If you, what section is it in? So I write it in the right place. Section 4. 13.4. So if you think about the vertical 13.4, is this our only page of it? Let me add a blank page. How about this? So if you think about it, let's say I went to a planet with a very small force of gravity, right? Now, the spring has a force of F equals negative kx. And so if I hang a mass on there, whatever mass it happens to be M on there, and I just let it go right there, it's going to come to a rest where? No, there's gravity. It's just a small gravity. So small gravity, small g, small acceleration of gravity. We're on the moon. And I put this mass spring and I hang it there. Where is it going to come to a rest? It's an E word. At equilibrium. It's going to come to a rest when mg, with that little g, equals kx. Right? You agree with me on that? All right. Now we go to a planet, come back down here to Earth, and we have a larger, I should say small and larger g. So this was the equilibrium on the moon. Same exact spring, same exact mass. Where's it going to come to a rest here on Earth? No, it'll be further down because why? Because mg is greater, right? And so therefore, this is going to stretch out. I didn't do a very good loopy job there. This is going to stretch out. We have a bigger mg, right? This is mg on the moon. This is mg on Earth. This mg is larger, therefore it's going to pull it down more, which means x has to get bigger in order for it to be able to counteract the larger force pulling it down. So the only thing that does is change, right? This was the equilibrium position here. All it did was change where the equilibrium position is, right? If I were to then displace this by like 2 centimeters or something downward, it would then bounce up and down 2 centimeters, down 2 centimeters up above equilibrium, correct? And over here, if I did 2 centimeters from this new equilibrium position, 2 centimeters down, 2 centimeters up, or 5 centimeters and 5 centimeters or whatever. So the only thing it does have an effect on switching where the equilibrium position is, but it doesn't affect what it does around that equilibrium position, right? Because if I pull it down 2 centimeters further, it's going to be a delta x from there of 2 centimeters, which is that same amount of force. And it's a delta x here. It's a change of that same 2 centimeters. And that force is proportional to that displacement. So it just changes where that equilibrium position is. It doesn't change how the spring actually acts by getting displaced the same amount from that new equilibrium position. Now, it is different. Let's say this equilibrium position is 10 centimeters, from the ceiling there, right? If I then take this one and stretch it down to 10 centimeters and let it go, I'm letting it go off of its equilibrium. It's going to vibrate. If I put this one at 10 centimeters and let it go, it's going to do nothing because that's its equilibrium position. So we're only looking at from where its equilibrium position is. Does that make sense? So G does change the equilibrium position, but it doesn't change what it does around that equilibrium position. So you can't say it has no effect. You can say it has no effect on what it does around the equilibrium position, but it does move the equilibrium position. But once you find that equilibrium position, you're good. It'll act the same. Unlike the pendulum, right? Anybody else? Yeah.
So for all these spring-like problems, or take elastic limit into account.
You just don't want to, you don't want to break the elastic. You don't want to overstretch it. If you stretch it to the point that it's deformed, then all bets are off. It doesn't work anymore. You've broken the spring. So yeah, like if you overstretch a slinky, you've changed K essentially. It's different now. Anybody else? No? All right, well, I don't think we have enough time to do anything else. We have like less than 2 minutes here. But if there's any other questions, you're welcome to ask me. If you don't want to ask in front of everybody, send me an email. We'll start chapter 14 next class, okay? Is it okay like this? I know we didn't get to solving any of those questions. We can do them for review or stuff, or you can look at those ones. They should be posted. Can y'all get to those questions in the notes on there, the other documents? It's not, okay, good. All right, yeah. What's that? I'll let you know after today. Still trying to get that figured out. Or I'll let you know probably by next lab class. Okay? But it's not due for 2 weeks. It's due in 2 weeks after your lab day.